Okay. Um, in today's lecture, we are going to continue from where we left in our last class. We started number theory in our last class, and we discussed a few topics on number theory. But before introducing anything new on number theory, let's move a little back and discuss about a problem we solved in our last class. I think you should remember the problem. I forgot the exact numerical values, the coefficients, but I think I solved a problem that looked like this. The question was solve this where x and y are integers. Can anyone confirm if these were the coefficients? I know the right hand side was 5. That I can remember. I can remember, but I do not remember exactly what the coefficients were. Okay, can anyone confirm me? Do any of you have the lectures with you at the moment?
Not at the moment, sir.
Okay, that's all right. Okay, I think these were the coefficients, and I think we found solutions that kind of we actually found a particular solution x, y. Forgot what the numbers were, doesn't matter. But at the beginning of the problem, I wrote 1 on the right hand side. Now, today we are going to discuss what we could do if we had 1 on the right hand side. We found out that the GCD of 185 and 395 is 5, and basically the process of finding GCD using the Euclidean algorithm helped us to solve this particular problem. And how so? Basically what we did was repeatedly expressed for example 395, we expressed 395 as in the form BQ plus R, right? So this was this 185 times something plus something, and then this was brought here, this was brought here. Again, we found something plus something. We kept repeating the process until at some point there is we found that the remainder is exactly 0, and at the point where this remainder was 0, the remainder of the immediate step before this step was declared to be the GCD. I am not going into the detail of the overall solution because you already have that. The recording is also posted in Discord, so you can revisit that solution. But this was the situation where we got 5 as the GCD, and the question also had 5 on the right hand side. But what if we had something like 1? What process can we follow? If we have 1, there is an easy answer for the question. That is, since 5 is the GCD of 185, let me rewrite the equation here. 185x plus 395y equals to 1. Since 5 is the GCD of these two guys, 5 is a common divisor. So we can take 5 as common out of the 2, right? So we can divide the left-hand side by 5, and we can be left with some quotient inside the bracket. But there is no 5 on the right-hand side, which means the left-hand side is divisible by 5, but the right-hand side is not. So this is a contradiction. So the situation suggests that there is no such x and y pair for which this equation can be true, because the same number cannot be divisible and not divisible by 5 at the same time, right? So for this situation, the solution, the final answer is there is no solution. So this is one variation of the problem has got another variation. So 185x plus 395 y equals to, if the right hand side is 15, then what should you do? In such cases, what we can do is find the GCD of these two guys, which should be 5 if I'm not wrong. Then this 5 can be expressed as a linear combination of 185 into some, maybe some k. I forgot, again, I forgot the solution, plus 395 times some L. Now, if you multiply both sides of this equation by 3, then you have 15 equals to 185 times 3k plus 395 times 3L. So 3k comma 3L is the solution of this equation. So if the right hand side is not divisible by the GCD, this is what I'm going to conclude of the discussion we had so far in today's lecture. If the right hand side is divisible by the GCD of these two coefficients, then we have solution. If the right hand side is not divisible by the GCD, we do not have any solution. And if we have solution, if the right hand side is exactly GCD, then it's an easier situation. If the right hand side is not exactly equal to GCD, but some multiple of GCD, then we have to do a couple of lines extra calculation to find the final solution. So k comma L is not the solution in this particular case. 3k comma 3L is the solution. So to summarize, if we have x plus by equals to c, if this is a Diophantine equation, linear, let me write a shortcut. If this is a linear Diophantine equation, then it has, please turn off your video. It has no solution if this, we have a shorthand notation for GCD, which is a comma b. If a comma b doesn't divide c, this is one conclusion. Another conclusion is it has if GCD of AB, we know that GCD of AB can be expressed as a linear combination sum AK plus BL. Then we have two cases. First one is two subcases to be more perfect. If C itself is the GCD, then solution is K comma L. And if C equals to some multiple M times the GCD, then solution is MK comma ML. But you can understand that the first subcase belongs to the second subcase as a special case where M equals to 1. So if I didn't even bother to write the first subcase, it would not matter, right? Because putting M equals to 1, the second subcase turns into the first subcase. Is there any problem so far? Please let me know. If not, then I'm going to proceed. Now, here is one thing. Do you think an equation that looks like this has just one solution? I mean, if you somehow manage to find that K comma L satisfies this equation, that is 185k plus 395l equals to 5. This would imply the solution set is just a singleton k comma l. Do you think so? Actually, this is not the case. But let me see. Let me show you how. um, say, for example, k comma l is indeed a solution. K comma l is indeed a solution. That means, say, for example, this line is true. K comma l satisfies the equation. Then, if I write something like this, k plus 395 by 5 times some random number t, any integer t. We don't care what t is. It's just an integer, plus 395 L minus 185 by 5 t equals to 5. So, I mean, for now, let's ignore the by 5. So let's just write this. Can you see that this equation is also true? If the equation in the box is true, then the one below should also be true. Because if you multiply the left-hand side, it becomes 185k plus 185 times 395t plus 395l minus 395 times 185t, and these two gets cancelled because they are the same number. So we are left with 185k plus 395l, which is exactly the left-hand side of the equation written in the box. So this should also be 5, which means this number and this number, that is k plus 395t, comma, l minus 185t, also satisfies as the solution. Putting x equals to this guy and y equals to this guy also satisfies. And we did not mention what t specifically is. All we mentioned was t is integer. For any integer t, this works. This means if you manage to find just one solution k comma l, you will be able to find infinitely many solutions of this form. Now the question remains, so we have just confirmed that there are infinitely many solutions. If there is at least one solution of a linear differential equation, there is actually infinitely many. But are these all of the solutions, or are there any more? This is the question. That is, can we conclude that the solution set is just numbers of this form, k plus 395t, comma, L minus 185t, such that t belongs to z? Are these all the solutions, or are there any solution outside of this solution set? This is the question. The answer is there can be more, actually, because if you divide by any possible divisor of 395 here and here as well, then divide them here and here, and the equation remains same. The only thing that matters is D has to be someone who divides 395 times 185. That is, after multiplying 185 with 395 by D, we need to have someone who is an integer. That's all we need to make sure. So any choice of D that make sure of this idea that the guy in this red circle-like area is an integer will do. But what are the possible values of D that makes this happen? Or rather, what is the highest possible value of D that makes this happen? The highest possible value of D, I think, is the GCD, right? Okay. I have a doubt here because not just GCD. We need to find the highest possible value of D so that 185 times 395 by D is still an integer. What choice of D should we make?
So should we take the LCM?
We should take the LCM. Okay, so D should be the LCM of 185 and 395. And if we choose the LCM, which means the least common multiple, does this ensure that this overall guy is an integer? What role does common multiple play here?
No, I think we have to take the GCD.
Okay, if here is the problem with GCD. If you take the GCD, greatest common divisor that divides both of them. So divide 395 by that number. You can still divide 185 by divide further to make I mean get lesser integers. Okay, let me give me a moment. Let me confirm what the coefficient should be. Give me a moment, please. Okay, I just checked, and I told that D has to be GCD from my memory, but I got confused on the way. But I just checked, and it is a GCD. And let me show you why I got confused and where it was the fault in the logic. Basically, the guy in this blue region need not be integer, but 395 by D has to be. I multiplied 185, but after multiplication, it has to be integer, no doubt. But it has to be integer even before multiplication, because this has to be a natural number, I mean an integer solution, right? This guy needs to be an integer, so that below 395 should be someone who is a divisor of 395. Again, this guy should also be an integer, so below 185 should be someone who is an integer. Now, what is the greatest integer that divides both 395 and 185? And GCD of them is the answer, right? So D is not LCM, but GCD. And yes, GCD is the correct answer. So finally, to conclude, all you have to do, if I write something in general manner, if you have AX plus BY equals to C, and somehow if you manage to find that X0, Y0 is a solution, then the solution set is going to be X0 plus, we have A here, so we have to multiply B by the GCD times T, comma, Y0 minus A by the GCD times T, such that T is any integer. So the logic that D is the highest possible value integer for which B by D and A by D are both going to be integer. Make sure that we have covered all the solutions. There are no solutions in between. We cannot optimize the situation further because we cannot have bigger denominator than the GCD D. So here D is the GCD of A and B. So using this method, we are going to solve linear Diophantine equations. So in your assignment, I am going to provide you one or two linear Diophantine equations, and you need to find the general solution. That means by general solution, I mean set of all the solutions. Please let me know if I was able to clear out the confusion we were dealing with.
Yes, sir.
All right. Okay. Let's move on to our next topic. So this is something from our last class that I wanted to stretch a little more than what we covered in our last class. And the new topic that we are going to study in today's lecture is two symbols: floor of a number and ceiling of a number. Their definition is pretty simple. Floor means the largest integer less or equal to n, which means if you have 4.1 and take floor, what integer is the largest that is less or equal to 4.1? The answer is 4. So if you take 4.8, the floor is going to be 4. If you take 4, the result is going to be 4. Ceiling is the exact opposite. Ceiling is the next smallest integer. So if you have 4.1, the ceiling is going to be 5. If you have 4.8, it's going to be 5. If you have 4, it's going to be 4. Because you can understand. Now, there is another symbol which looks like this. It looks exactly like a third bracket, but this means the closest integer. So this is 4 and this is 5. Of course, there is a confusion regarding 4.5. And the idea is if it surpasses 0.5, it's going to be rounded to the next integer. Otherwise, it's going to be the immediate integer before the number. But sometimes in some texts, they follow the convention that it should be 5 whenever we have 0.5 or more. So in some texts, they consider 4.5 is equal to 5. And this is just convention, and we are going to follow this convention. Now, I want to clear a confusion that you may encounter while reading the book by Barnard and Child. In Barnard and Child, okay, I should write the names of the symbols. This is floor and this is ceiling. I think I'm not sure if I made any mistake in the spelling of ceiling, but you can understand, I think. But
Sir?
Yes.
Sir, could you write the book name in the chat?
The name of the book is written in multiple places, actually. Barnard and Child.
Oh, Barnard. Okay.
The name is available. In fact, the book itself is available in PDF format in the Google Sheet I provided. All right.
Okay, sir.
And okay, have you gone through the Google Sheet I provided? Have you gone through the Google Sheet I provided? Who asked the question?
Me.
Okay. Did you go through the Google Sheet I provided in Discord?
No.
Okay. Please do. You'll be glad to have the Google Sheet. All right. The detailed lecture plan along with exercise problems are provided there. and I have provided a download link for the drive link for both the books. I'm going to follow there as well. Anyway, this symbol is called floor, and this symbol is called ceiling. Please excuse me if I made any mistake in the spellings, but you are going to get confused when you go through the number theory chapter of Barnard and Child, because they used in that book, this means floor. Now, this book was written a long time ago, and this is not the convention modern mathematicians follow. So please beware of the mix-up of the symbol, all right? Please don't get confused when you go through the textbook. Please stick to this symbol I just wrote down here. Now, floor and ceiling are pretty silly symbols, but they can be very useful. Looks are not, sometimes looks are not representative of what someone is capable of, right? So here are some properties that are related to these symbols. For example, one property is, you can understand that if you have a number, for example, 4.1 and another number, say 2.6, if you add the floor of these two, you get 4 plus 2 equals to 6. But if you add the numbers first and then take the floor, you get 6.7. Okay, I was trying to show something different. Give me a moment, please. 6.7. Okay, I'm going to change one of the numbers to establish what I want to do. So instead of 4.1, let me use 4.7. So the first line is still true because the floor still remains 4 for 4.7. But if you add 4.7 and 2.6, what you get is 7.3. And the floor of 7.3 is 7. So you can see that floor is not someone that we can just distribute over numbers. So, but in the example we just wrote before writing 4.7, you have seen that in this case, 4.7 plus 2.6 floor, this is actually greater than individually 4.7 plus 2.6. But if you tweak the numbers or change the numbers in a particular way, you can get situations where you get actually equality. But you are never going to get less than, because you can understand that technically, when you take floor, you reduce the number by some amount, some fraction. So here you are reducing in two places, but on the left-hand side, you are reducing in just one place. So the right-hand side is going to be either less or at best equal, but never going to be greater. That's for clear, right? So if we combine the two ideas, we can easily write that any number x plus y floor is going to be greater or equal to floor x plus floor y. So this is something we can just prove by experimenting with different examples. In Barnard's book, they provided a proof, but there is a little bit problem with the proof because that proof is only applicable for rational numbers. But you can understand that we can always deal with irrational numbers while taking floor, right? We can take floor of irrational numbers. This is floor of 1.41, blah, 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 blah. So the floor value has to be 1. The proof in Bernard's book is only applicable for rational numbers, and that is why that proof is not a general proof. Instead of proving in general, I just like to give the intuitive idea behind the inequality we just wrote. Okay, another idea that we are going to discover, which is related to floor function. This one is pretty interesting, actually. Instead of writing the idea first, let's demonstrate with an example problem, actually. Let me write the problem statement. Find the highest power of 5 that divides 100 factorial. This is a pretty common and interesting question. Those who are familiar with Mathematics Olympiad must have already solved problems like this 1,000 times already. The problem is pretty interesting. What is 100 factorial? 100 factorial is 1 times, you are familiar with the factorial notation. This is 1 times 2 times 3 times up to 100. Now, this number is a big number. This is a huge number. And this huge number, in the string of products here, you have multiple 5 in multiple places. At some point you get, after 4 you get 5. At some point you get 10, which is also divisible by 5. At some point you get 15, then 20, then 25. 25 is divisible by not only 5, but 5 square. So if you multiply all of those numbers, there must be a pretty high value as a power in 5 you can put that still divides 100 factorial. But what is that exact number? This is the question. And we can find the answer using the floor notation. Let's see how. First of all, let's consider a smaller value. Let's consider 7 factorial. I mean, let's consider 12 factorial. Just for experimentation. 12 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 times 11 times 12. So where are the places where that you can locate 5s? One is here, another is here. So by observation, you can see that 12 factorial can be divisible by 5. You can divide 12 factorial by 5, and you can divide 12 factorial by 25, but no further. 12 factorial is not divisible by 125 because you cannot find 3 5s here. We have just 2 5s, one here and one here. 10, which is actually 2 times 5. So you have 2 5s in this string. So by observation of this example, you are pretty interested to just, interested to find out just how many 5s, how many multiples of 5 are there in between the numbers from 1 to 12. And that result is pretty simple. If you divide 12 by 5, there is exactly one guy who is a multiple of 5 in every 5 integers, right? In a sequence of consecutive numbers. So 1 in every 5 integer is going to be 5 if you write them consecutively. That is why you divide 12 by 5 and take floor. If you divide 12 by 5, you get 2.4. So this 2 means you got up to 10. And this 0.4 means you were on the way to get to 15, but you were not quite there, right? So this row is going to be cancelled. And that is why we took floor function to get 2. But if you treat 100 factorial in the same way and try to write that, the answer is 100 by 5 floor, then you are not going to be correct. The answer is going to be wrong because as you can see, if instead of 12 factorial, you just wrote 28 factorial, then there's something that's going to there's going to be a situation which was not quite present in case of 12 factorial. And what's that? You got 5, then at some point you got 10, at some point you got 15, at some point you got 20, but finally at some point you got 25. Before 25, all the multiples of 5 were divisible by 5 only, but 25 is divisible by 5 square. You have 2 5s here as divisors. So now you have to find out the places where you considered multiples of 5 who were also multiple of 25. And for that, if you also count those, that's going to be 100 by 25 floor, because you are going to find a 5 square in every 25 integers, right? One is 25, the next one is 50, the next one is 75, the next one is 100, etc. But now you know that there may be a situation where you have 5 cube. So you have to find the numbers which are divisible by 5 cube. And fortunately, from 1 to 100, there is none. But even if you wrote a term in a similar manner, 100 by 125, this is not wrong either, because this is actually 0. It contributes nothing to the summation. So the final answer is 20 plus 4 plus 0. You could just go on and write 125 times 5 is 625. You could just unnecessarily write this. You could. It would provide nothing but 0. So the final answer is 24. So the highest power of 5 that divides 100 factorial is actually 25 to the power 24 is the highest power of 5 that divides 100 factorial. Please, is there any confusion understanding the solution of this problem?
No, sir.
Okay. So let's generalize the idea to write this. The highest power of a prime P, which is contained in n factorial, is equal to floor of n by p plus floor of n by p square plus floor of n by p cube. You have to go on and on until you start getting 0 as the floor value. That is, you have to continue until p cube exceeds p to the power of p exceeds n, right? So this is another idea that we can implement using floor function. Now we have a theorem. It's theorem 9 in Barnard and Child's book. The theorem states that basically this section number 9 contains a multiple of theorems. The first being the product of any n consecutive integers is divisible by n factorial. So any random n consecutive integer. So you can start with just m plus 1, continue m plus 2, m plus 3, take product of all these consecutive integers, and you have to take n of them. You started with m plus 1, so the nth guy has to be m plus n. So according to the claim of the theorem, the first theorem, this product is divisible by n factorial, which means if you divide this by n factorial, you are going to get an integer. This is the claim of the theorem. Now, I'm going to solve it in two ways. First, I'm going to solve using a very straightforward idea from permutation and combination. And then I'm going to use a method that I'm going to focus on in today's lecture, actually the one that uses the idea of floor function. First, let's do the straightforward version. You can see that this expression could be directly written as m plus n factorial by n factorial. I could write this, but it's not correct, so not yet actually, because to write m plus n factorial, I had to start from 1. But instead of 1, it started from m plus 1. So I have a few numbers short here. What are those numbers? 1 times 2 times 3 up to m. So the numbers that are absent here is 1 times 2 times 3 up to m. And that guy is just m factorial. So I have to balance by writing an m factorial at the denominator. Then it would be correct. Now, those of you who are already familiar with permutation and combination, you know that this is nothing but m plus n c n. And the number of choice from m plus n objects you can make of n objects is an integer. So this is an integer which directly proves that our claim is true. But as I have already mentioned, I am not interested in this proof. My interest lies in proving using the floor notation. So let's get there. So our expression is again m plus n factorial divided by m factorial n factorial. I want to prove that this expression is an integer. So in other, saying that this is an integer is equivalent to saying that any prime that divides the denominator, for example, any prime p that divides the denominator, also divides the numerator, and not only that, the highest power of p that divides the denominator has to be lesser or equal to the highest power of p that divides the numerator. I think you understood what I said. What I meant is, let's mention by an example. So you have 24 by 8, 24 by 12. Now, to make sure that this fraction is not really a fraction but an integer, I have to make sure that find a prime that divides 12. 2 divides 12. But what is the highest power of 2 that divides 12? Answer is 4, that is 2 square. So in 24, how many 2's are there? 2 cube. So square is lesser than cube. So the highest power of 2 that divides 12 is actually lesser than the highest power of 2 that divides 24. That is why the 2 square is vanished. The 2 square is cancelled. What's another prime that divides 12? 3. And what's the highest power of 3 that divides 12? It's 3 to the power 1. What's the highest power of 3 that divides 24? It's also 3 to the power 1. So we get the cancellation. So we have to make sure that the power of p, that highest power of p that divides the numerator, is actually greater or at worst equal to the highest power of the prime that divides the denominator. So let us choose a particular prime p, which is an arbitrary choice. We don't mention what p is. P is an arbitrary choice. Now, the denominator is m plus n factorial, and how many p divides m plus? What is the highest power of p that divides m plus n factorial? We have already found the answer, and the answer is divide this by p and take floor plus divide this by p square and take floor plus divide m plus n by p cube and take floor. We have already solved such a problem and go on. Now, we have seen that this guy actually is greater or equal to floor of m by p plus, let's write below, plus floor of n by p. I just used the idea. I proved using example somewhere here. I use this idea. If you distribute the floor over the integers in between under summation notation, you have to put a greater or equal to sign. This is exactly what I did here. I put greater or equal to sign and distributed the floor sign over m by p and n by p. Now let's get here. We can do the same for the second floor function as well. So we can just write this plus this. Same for the third one. Okay, we have to write n here and n here and so on. Well, is there any problem up to this point? I hope not. Now, you should be able to see that this series above denotes the highest power of p that divides n factorial, and this denotes the highest power of p that divides n factorial. So their summation denotes the highest power of p that divides n factorial times n factorial. So this is the relation that makes sure of the idea here. So we are confirmed that this guy is indeed an integer. The next topic I'm going to cover is method of induction. Most of you are already familiar with the idea, but I'm going to describe the basics anyway. The idea goes like this. If a statement, let me show you by an example. We know there is a well-known formula that looks like this. Now, proving the method of induction works like this. Assume that, so this is an equation or a claim or anything. Assume that this is true for n equals to m. Then using the assumption, prove that this is true for n equals to m plus 1. Now, if you can manage to do this task, you did not make sure that the equation is true for m. You did not make sure that the equation is true for m plus 1. You did not make sure either of the cases. What you made sure is, if somehow the given statement is true for m, it is going to be true for m plus 1 as well. So basically, you prove that there is a cycle involved. That somehow, if you can manage now, that if you can manage to prove that the equation is true for n equals to 5, then using the fact here, if it's true for m, it is going to be true for m plus 1. So since this is true for 5, it's going to be true for 6. Now use the same idea repeatedly for 6 again, then it's going to be true for n equals to 7 and so on. So if you start with n equals to 5 and use this idea, you can make sure that the equation written in star or the statement written in star is true for every integer greater or equal to 5. Now, generally, it's natural that you are going to start, should be interested to start with n equals to 1. So the value of n that you are going to start with is generally called the base case. And the base case is not always n equals to 1. You can it can be required to start with some other numbers as well. That is why I mentioned about n equals to 5 earlier. But in most cases, the base case is related to n equals to 1. Now, you can, I think most of you have already solved different problems using mathematical induction. Here we have a problem that we are going to solve using mathematical induction. The problem goes like this. Show that 2 to the power twice n minus thrice n minus 1 is divisible by 9. In most other, just like most other cases, you have you can solve this problem in multiple ways. My concern is the way that involves mathematical induction, but let me show you an easier way first. You can just write 2 to the power 2n minus 3n minus 1 as 3 minus 1 to the power 2n I mean 3 minus 1. I have a better option. 2 to the power 2n is just 4 to the power n. So we can just write 3 plus 1 to the power n minus 3n minus 1. Now use binomial expansion. We have 3 to the power n plus 3c1 into 3 to the power n minus 1 plus 3c2 into 3 to the power n minus 2 and so on. At some point, we are going to get why did I write 3c1 and 3c2? I had to write nc1 and nc2. So nc1 and nc2. Anyway, so at some point we are going to get 3 to the power 1 with the coefficient n, and finally 3 to the power 0 with the coefficient 1. So this is just the binomial expansion, and we have minus 3 and minus 1 here. And if you observe closely, you can see that this is plus 3n and this is minus 3n. This is plus 1 and this is minus 1. And in all the remaining terms, the least power of 3 is going to be square. So the entire expression starting from here to here is going to be divisible by 9, because you can take the least power of 3, which is 3 square, common out of the bracket. So this is an easy solution where you can show that this expression is divisible by 9. But as I have said earlier, I'm more interested in using mathematical induction. And I can, technically, I can push you to use mathematical induction by just writing, show using mathematical induction that this guy is divisible by 9. So I have the liberty to do that in exam questions, of course. Let's assume the expression to be a function of n. This is 2 to the power 2n minus 3n minus 1. Find out f of n plus 1, which should be 2 to the power 2n plus 2 minus 3n minus 3 minus 1, which should be 4 into 2 to the power 2n minus 3n minus 3. I'm interested in subtracting f of n from f of n plus 1. If I do that, I have 4 times 2 to the power n here and just 1 times 2 to the power n here. So I have 3 into 2 to the power 2n. The 3n gets cancelled and we have minus 4 and plus 1. So minus 3 here. We can just take 3 out of the bracket. We have 2 to the power 2n minus 1. Now, the right-hand side is divisible by 3. Then, so should be the left-hand side, right? So we are sure that this left-hand side, f of n plus 1 minus f of n, 3 divides this entire expression. Now you can understand that individually fn and fn plus 1 may not be divisible by 3, but their subtraction or their difference is divisible by 3. This is the idea we can see here. Now, you should be able to see that if 3 divides f of n, then 3 must divide f of n plus 1 as well. Because it's not possible, a situation is not possible where fn is divisible by 3, fn plus 1 is not, but still the overall difference is divisible by 3. This is not possible. If this part is divisible by 3, this part has to be divisible by 3 as well, so that the overall difference is divisible by 3. So if 3 divides this expression, then 3 divides this expression. Now you should be able to see that we have a concept of induction here. If you manage to prove that f of 1 is divisible by 3, then this idea will make sure that f of 2 is going to be divisible by 3, and iteratively it would mean that the next f is also divisible by 3. So what is f of 1? F of 1 is 2 square minus 3 minus 1. So 4 minus 3 minus 1, which is 0. And 0 is divisible by anybody other than 0. So 3 divides f of 1. So we now, since 3 divides f of 1, inductively we have showed that 3 divides f of n for every n. So therefore 3 divides f of n for all n in the set of natural numbers. So this is how induction works, and there is another solved example in Bernard and Child's book, which works in a similar way. So there is going to be some number theoretic ideas that you may need to prove using mathematical induction. Some of them have alternate solution. In some of for some of the problems, it would be impossible to solve in any other way than using mathematical induction. This is the content I prepared for today's lecture. And in our next lecture, I'm going to continue with some other topics like equivalence relation, modular arithmetic, and congruence. Okay. So for now, this is all. Please let me know if there is any question from anywhere of any topic in today's lecture.
No questions, sir.
Okay, so then that would be all. I'm going to close the meeting. But before that, I have an announcement. First, let me stop.